Dear students, in this video we are going to study an important theorem of this unit which establishes the relationship between a vector space and its dual space. Before going to the theorem, let us recall some definitions and results. Let BF be a vector space, then the set LBF of all linear functionals on vector space V is a vector space over the field F under the operations of addition and scalar multiplication defined respectively as T1 plus T2x equal to T1x plus T2x for all T1, T2 in LBF, x in B, and alpha T1x equal to alpha T1x for all alpha in F, T1 in LBF. And this space is called dual space or conjugate space of V. We will denote this space by B star usually. Let UF and VF be two vector spaces and S be a subset of U. Let F from U to V and G from S to V be two maps such that Fx and Gx are equal. That is Fx equal to Gx for all x in S. Then the map F is called extension of G to the whole of U, and the map G is called restriction of F to S. And we denote it like this: F restricted to S equal to G. Then a theorem: every map from a basis of a vector space can be extended to a linear transformation on whole of the vector space. Further, if two linear transformations are equal on a basis of a vector space, then they are equal on whole of the vector space. That is, if two linear transformations agree on a basis of a vector space, then they agree on whole of the vector space. Again a theorem: let S be the set containing vectors x1, x2, so on up to xn. Let it be an ordered basis of an n-dimensional vector space Vf. Then, for any ordered set T containing scalars alpha 1, alpha 2, so on up to alpha n, there exists a unique linear functional f on B such that f at xi equal to alpha I from 1 to so on up to n. Now let us come to the main theorem, which states that the dual space B star of an n-dimensional vector space Vf is n-dimensional. Let us come to the proof of this theorem. Let S be the set containing vectors x1, x2, so on up to xn, and let it be an ordered basis of V. Then, by previous theorem, there exists a unique linear functional f1 on B such that f1 at x1 equal to 1, f1 at x2 equal to 0, so on up to f1 xn equal to 0, where 1, 0, so on up to 0 is an ordered set of n scalars. In fact, for each I from 1 to so on up to n, there exists a unique linear functional fi on B such that fi xj equal to 0 if I not equal to j, 1 if I equal to j. For example, if this ordered set is 0, 1, 0, so on up to 0, then we get a linear functional f2 on V such that f2 at x1 equal to 0, f2 at x2 equal to 1, so on up to f2 xn equal to 0. Let S star be the set containing linear functionals f1, f2, so on up to fn. Since f1, f2, so on up to fn, these are linear functionals on B, so these are elements of B star. And since S star is a set containing these elements f1, f2, so on up to fn of B star, therefore S star is a subset of B star having n elements. We shall show that S star is a basis of B star. To show that S star is a basis of B star, we have to show that S star is linearly independent subset of B star and S star spans B star. First, we claim that S star spans V star, that is L S star equal to B star. To prove the claim, take an element f in B star. For each I from 1 to n, let f be defined like this. F at xi equal to alpha I belongs to f. Now take G as a linear combination of f1, f2, so on up to fn by scalars alpha 1, alpha 2, so on up to alpha n. Since G is linear combination of elements f1, f2, so on up to fn of B star, and B star is a vector space, therefore G is also an element of B star. And G at xi equal to some I from 1 to n alpha fi at xi, which is alpha I fi xi. Since fi xj is 0 for I not equal to j, and fi xi equal to 1, therefore this is equal to alpha I, and which is equal to f xi, because alpha I equal to f xi. So this holds for every I from 1 to so on up to n, and it means that f and g agree on a basis S of V. And we know that if two linear transformations agree on a basis of a vector space, then they agree on whole of the vector space. Therefore, F is equal to G, because F and G are agreeing on a basis of a vector space. And since G is an element of B star, therefore F belongs to, and G is an element of B star, and G is a linear combination of f1, f2, so on up to fn, therefore F belongs to Ls star, and this implies that Ls star equal to V star, that is S star spans B star. To show that S star is linearly independent, take scalars beta 1, beta 2, so on up to beta n in F, such that linear combination of f1, f2, so on up to fn by scalars beta 1, beta 2, so on up to beta n is O, where O is a linear functional on V defined like this: Ox equal to 0 for all x in V. That is, O is 0 linear functional. Now some I from 1 to n beta fi equal to O. This implies that some I from 1 to n beta fi at x equal to Ox for all x in V. Because quantities on both sides of this equation, these are linear functionals, and two linear functionals are equal, Therefore, they are the image of any element x of v under these two linear functionals is also equal. And this implies that some I from 1 to n beta I fi x equal to 0 for all x in v, because Ox equal to 0. And this implies that some I from 1 to n beta I fi xj equal to 0 for j from 1 to so on up to n. Here in particular we are taking x equal to xj. Since this thing happens for every x in v and xj is an element of v, so in particular this thing happens for x equal to xj also. So we are taking x equal to xj in particular here. So some I from 1 to n beta I fi xj equal to 0 for j from 1 to so on up to n. And this implies that beta j equal to 0 for j from 1 to so on up to n, because fi xi is 1 and fi xj is 0 for I not equal to j. And this implies that all the scalars beta 1, beta 2, so on up to beta n are equal to 0. And so f1, f2, so on up to fn, these are linearly independent vectors of vector space V star, and this implies that S star is a linearly independent set. Since S star is linearly independent set and it spans V star, hence S star is a basis of B star. And since S star contains n elements, therefore dimension of V star is equal to n. Thus dimension of V is equal to dimension of B star. We know that two finite dimensional vector spaces are isomorphic if and only if they have same dimension. Since dimension of V is equal to dimension of V star, therefore by this result B is isomorphic to B star. Now a definition: let BF be a finite dimensional vector space with x1, x2, so on up to xn as its basis. Then the basis f1, f2, so on up to fn of B star such that fi equal to 0 if I not equal to j, 1 if I equal to j, is called the dual of the basis x1, x2, so on up to xn of V, or simply the dual basis of B star. In next video we will give an example of dual basis of a vector space.